Alright, so this is the first of 2 videos on the singular value decomposition. So in this video, what I'll generally talk about basically is just sort of what the singular value decomposition is, just computationally, and how we go about constructing it. And then in a second video, I'll just give some examples and walk through those and point out the importance in the matrices that result. So, for an intro, I just want to comment that given a matrix, it's very often the case that we'd like to factor that matrix, meaning we'd like to write that matrix as a product, right? So we'll say it's often useful to factor a matrix, which we'll say meaning to write it as a product, specifically as a product of other matrices. So for example, an example you may have seen in linear algebra before is if you diagonalize a matrix. So we'll say given a matrix A, to diagonalize it, so this means to write it as a product. Right? So to diagonalize it would mean to write it A equals P D P inverse. And in such a case, this would be with D being diagonal and P being invertible. So in other words, D is the diagonal matrix and P is an invertible matrix. And it's a fact from number theory or a fact from linear algebra that this can be done by using the eigenvalues and eigenvectors of A. I won't go into how exactly it's done, but this can be done using the eigenvalues and eigenvectors of A. And this is useful because, for example, this is a very simple case. If you want to do something, if you wanted to do something like a to the 10, like just for the sake of argument, right? If you could diagonalize this matrix, then when you do this calculation, when you raise it to the 10th power, you get a lot of cancellation. You get cancellation of all these P and P inverses. So at the end you get P D to the 10th P inverse. Doing a diagonal matrix to a power is easy. So this is a particularly nice result. So if this is all a bit fuzzy, that's okay. The key thing I want you to remember is that writing the matrix as a product, right, factoring it, in other words, so like we've done right here in blue, right, is useful. And so if you can accept that writing a matrix as a product is useful, then what that means is if there are other ways to write a matrix as a product, then maybe those would be useful too. Right? So that we could say this, are there other ways to write A equals a product of matrices, which is useful, or which are useful? So the short answer is loads. There's lots of sort of decompositions is the phrase that's used. So the one we'd like to focus on specifically is what's called the singular value decomposition. So what I'll do here is I'll define the singular value decomposition. So I'll say like to find a singular value decomposition means to find matrices that have the following properties, just like we did on the left. And then what we'll do is we'll talk about how you go about doing this. And we won't delve into too many details. You can look in a class textbook or any other textbook you like for all the gory details about all the technical stuff, but we'll point out the important things. And then when we've seen that, then I'll stop this video, and in another video I'll do some examples and point out what's critical about what we found. So here's our definition. So given the matrix we start with doesn't need to be square, so we'll say given an m by n matrix A, so this means m rows by n columns. The singular value decomposition, which will here and forever be abbreviated SVD. Singular value decomposition of A is, let's say, a product A equals U sigma V transpose, where the following are true. Right? So U will be an m by m orthogonal matrix. V will be an n by n orthogonal matrix. And sigma, which looks like a sigma for sum notation, but it's not. It's just another matrix. This is an m by n diagonal matrix. Now, these are two terms that may not be familiar to you. An orthogonal matrix, well, it could be familiar, but you could just need sort of a jogging of the brain, and what it means to have an m by n diagonal matrix, which is a diagonal matrix which isn't necessarily square. So just two definitions in case you've forgotten. So a matrix is orthogonal if the columns of the matrix are unit vectors which are all perpendicular to one another. So we'll say a matrix is orthogonal if the columns are all unit vectors which are perpendicular to one another. So equivalently, it's the same as saying that the matrix times its transpose is the identity, right? So equivalently, we can say that U is orthogonal if and only if U transpose equals U transpose U equals I. So the critical thing though to remember out of each of these different ways of looking at it is that the columns are all unit vectors that are perpendicular to one another. That's the critical thing. The other fact is sort of equivalent to that, but maybe not the best way of thinking about it. So the other definition is that an m by n diagonal matrix, this is nothing more than an m by n matrix such that the only non-zero entries are like the 1, 1 entry, the 2, 2 entry, etc. So it's a matrix for which the only non-zero entries could be the 1, 1, 2, 2, 3, 3, etc. Those entries. So this is the definition of a singular value decomposition, is to find such a thing. Let me box that in and make that sort of really, really relevant, right? So just to find something that looks like this, where those three matrices satisfy this property, or these properties. Now let me do this. Let me clear the screen. I'll give you an example of a singular value decomposition. I'm not going to say for right now where these matrices came from. I just want to show you like a product of three matrices and say like, look, if you multiply these, you get the original matrix. and show that these matrices on the right hand side satisfy the conditions that are given here. So let me clear the screen and do that. So for example, so let me pause the screen, pause the recording and fill these in, because there are a few matrices to do and there's no reason for you to watch me fill in these numbers. All right, so like I said, don't worry about where these came from right now. Right? If you were to grab MATLAB, or if you did this by hand, if you did the calculation on the right hand side, you would find that this product holds. Also, I just realized I messed up a matrix in there. Hold on, let me fix this. All right, now we're fixed. So, but I just want to point something out, and I won't do these calculations, but you can look at them and just sort of observe or sort of believe that they are what I claim them to be, right? So the things the things that I claim are the following. If you look at the matrix U, that this column is a unit vector. If you take its magnitude, you will get 1. Right? This column is a unit vector. Those two columns, those are perpendicular. If you take the dot product, you will get 0. Right? Over in V, this is a unit vector. This is a unit vector. Again, these aren't obvious, but you recognize the calculation, so that's okay. This is a unit vector. If you take any two of them and take the dot product, you will get 0. They are perpendicular. And last but not least, if you look at the one in the middle, the only entries that are non-zero are on this diagonal. Right? Now, there's an extra column of zeros on the right-hand side. That doesn't matter. The point is here that the only non-zeros are 1, 1, 2, 2. So this is a singular value. This is an example of a singular value decomposition, right? To be precise, this is a singular value decomposition of the matrix A. Of course, the first question, there are several questions, is where did I get these? And the second question, which for us is maybe more relevant, is how are they useful? So the first of these questions, I was going to do it in this video, but I'm actually going to split this off. This I'll put in the next video. In the next video also, I'll do some more examples. In other words, I'll in fact work out this one. Like we'll show where these specific values came from. And then how they're useful, lots of ways. We'll look at several of these in this class. So let me stop this video where we're at, and then what I'll do is I'll sort of talk about how we come up with the U, the sigma, and the V. And we'll do this specific example. And I think probably the more examples we'll do in another video. We'll make it 3 instead of 2. And then we'll see how, and then as we go forward, we'll see how these are useful.